Hello, my name is Hyunkoo Lee, and today I'll introduce the paper about consistent video depth estimation, which is submitted for SIGGRAPH 2020. Before we begin, please watch these three short videos. Last one is the original video source, and the middle video is a reconstruction of the 3D space based on the original video, and showing the different colors depending on the depth of each pixel. Using this jet value of pixels also makes us able to apply this kind of visual effect like as the right video. Isn't it interesting? So this is the main point of this paper, the 3D scene reconstruction from sequences of images and videos. And it was challenging problem from past. The main issue of 3D reconstruction is how can we assume the z-axis value from the 2D information sources like image or video. Of course, there were many precedents to solve these problems, and it can be divided into two big categories. First one is traditional SFM reconstruction methods, and second one is learning-based methods. Traditional SFM reconstruction methods combine sparse structure from motion with dense multiview stereo. In result, it usually produces geometrically accurate reconstructions. However, during the process, it takes regularizing with heuristic smoothness priors, and it makes drops of pixels with low confidences. So, it produces holes in the reconstruction result. You can see the white and black holes in both of these depth images produced by SFM reconstruction methods. Recently, learning-based methods that operate on single images are emerging. They don't need heuristic regularization, so they can avoid hole problem and can synthesize more plausible depths and can work in scenes where traditional methods were not applied well, like dynamic scenes. But the estimated depth often flickers erratically due to the independent per frame processing. You can check result image is much clearer than previous one, both in left and right images. However, image's depth is not consistent in every frame. Horse's body seems to be flicking in the second frame of the left image. Also, it is not metric, which means not related to the true depth by single scale factor. By combining these two methods, the study tried to eliminate each of the problems and revive only the strengths to get clear and geometrically consistent result using monocular video, without multiview sources. You can see the horse image's result is much clearer, geometric features are retained for every frame, and no holes in the horse's body. Watch out for the pronunciation. Their method's pipeline consists of two big processes, pre-processing and test time training stage. In pre-processing stage, traditional structure from motion SFM reconstruction pipeline is executed by using CalMap. Then apply mask RCNN to segment people and remove their regions for more reliable key point extraction and matching, since people account for the majority of dynamic motion. At last, they estimate dense correspondence between pairs of frames using optical flow and conduct camera calibration. Optical flow describes whether pixel pair indicates same scene point or not. It makes to measure the scale of scene and match the scale with SFM reconstruction and learning-based model. Secondly, in the test time training process, they make set of frame pairs and check whether those frames are geometrically consistent. To evaluate the consistency, we have to consider the geometric laws between two frame pair using optical flow. It starts with this clue. If the flow is correct and the flow displaced point is identical to the depth reprojected point, then the depth must be consistent. Therefore, it calculates the two aspects of geometrical laws, spatial and disparity laws, and backpropagate these consistency errors through the network to refine network to produce depth that is more consistent than before. Spatial laws means differences between in frame pair, original frame's pixel projection in pair's frame, and flow displaced point. On the other hand, disparity laws similarly compares differences between camera coordinate systems' disparity of frames. Through these pipelines, they implemented the monocular depth estimating system and evaluated it comparing with previous models. For dataset, they used custom stereo videos, including 4 static sequences and 3 dynamic ones. Videos were captured with Hyunkoo cam and cropped the middle part with resolution 1920 multiplied by 1440 pixels to exclude the severely distorted areas. The length of the captured video ranged from 119 to 359 frames. Also, for completeness, they provide quantitative comparisons with the state-of-the-art depth estimation models on 3 publicly available datasets: TOM dataset, ScanNet dataset, and Kitty dataset. There were 3 evaluation metrics: photometric error, EP, instability, ES, and drift, ED. Photometric error is RGB difference of reprojected pixels based on estimated depth, and instability is instability of estimated depth maps calculated by Euclidean distances of the 3D points for each pair of consecutive frames. Lastly, drift is case when point drift away, so we measures how spread the 3D points in across time between not consecutive frames. This graph is the experiment result. Upper graph is conducted on dynamic scenes, and downward ones are conducted on static scenes. From left to right, graph's y-axis expresses the cumulative errors, photometric error, instability, and drift. X-axis simply means how many samples are applied. Therefore, as experiment executed for more samples, error increase. Their models are plotted in red color, and you can see their model's performance is much better than other traditional state-of-the-art depth estimation algorithms, especially in instability and drift aspects. It means their geometric consistency is maintained well and stable. This is the visual comparisons of their method and traditional state-of-the-art methods. As you can see in B, CalMap is traditional multi-view stereo method. It produces accurate depths, but there are many holes. C and D are learning-based single-image depth estimation approaches and produce dense, plausible depth maps, but flickering occurs over time. Video-based approach, E, can avoid flicking problem partly, but suffering from drifting. However, their method's result, F the most right one, produce geometrically consistent and flicker-free estimation which looks best from among images. You can see same features on these results from different sources too. Like this. Finally, Using this geometrically consistent depth estimation result, they could apply these kinds of various video effects naturally. To sum up, the main purpose of the research was to make geometrically consistent 3D reconstruction algorithms, combining with traditional SFM methods and learning-based methods on each frame for monocular video source. And as a result, the method has some advantages and disadvantages. For advantages, their result is geometrically consistent for whole video, all frames. In other words, there are less flickering and hole problems. Also, they can cover not all but some of dynamic motions of the scene, like shaking hands, and work simply for monocular video source. So, comparing with previous approaches, they produce more high-quality estimation for many cases. However, their method is highly dependent to CoMap in pre-processing stage, which estimates the camera pose from a monocular video. Therefore, it is affected by this poses error. Also, it can't handle extreme dynamic motions like previous methods, and speed is slow since their test time training step takes about 40 minutes for a video of 244 frames and 708 sampled flow pairs. In conclusion, they made noticeable improvements, but there are still many tasks left for 3D reconstruction. Thank you for listening. Thank you.